Let me ask you something that sounds simple enough to answer in one breath. How big is the universe? And before you give me the answer that probably jumped into your mind, I want you to catch it in the act. Watch how quickly it appears. Infinite, endless, stretching forever. No wall, no border, no last galaxy, no final darkness where space gives up and stops. It is such a clean answer that it almost feels scientific, but that is exactly why I do not trust it immediately. Because in physics, the answers that feel cleanest are often the ones we have not examined carefully enough. You see, infinity is a very convenient word. It lets you close a door without looking inside the room. If the universe is infinite, then there is no outside, no edge, no awkward question waiting behind the curtain. You can say it goes on forever and feel as if you have solved something when really you may have only avoided the harder problem. I do not blame you for doing that. We all do it. The mind likes a smooth picture. It likes a universe that behaves politely, a universe that does not force it to invent new categories just to think clearly. But let's be honest with each other. Nobody has measured infinity. Nobody has sent a probe far enough to report back. Yes, still going. No edge yet. What we have measured is the part of the universe whose light has reached us. What we have built are models, not magical windows into all of existence. And that distinction matters. It matters because the sentence, "the universe is infinite," sounds like knowledge. But it may be only a habit wearing a lab coat. I learned to be suspicious of habits like that from very small things. Once, I was watching a spinning plate wobble on a table, and the ordinary answer was that friction would slow it down. The motion would die, and that would be the end of the story. But if you look carefully, really carefully, the plate is not just slowing down. It is exchanging energy with the table. The air, tiny vibrations, little losses you normally ignore because your everyday brain does not need that level of precision. Physics begins the moment you stop saying obvious and start asking, what exactly is happening here? Now apply that same discipline to the universe. Do not let the size of the question frighten you into accepting the easiest answer. When you say space goes on forever, what are you actually saying? Are you saying the data demands it, or are you saying your imagination runs out of better pictures? Because those are not the same thing. Your imagination was trained on rooms, roads, oceans, mountains, and horizon. It knows how objects end. It knows how surfaces stretch. It does not naturally know how space itself might be shaped. That is where the trouble begins. The universe may not be infinite in the simple way you pictured. It may have a size. It may have a topology, a way of connecting back to itself. It may have a boundary that is not a wall, not a cliff, not a glowing line at the end of the stars, but something far stranger, a limit written into the structure of space itself. And I want you to notice how uncomfortable that feels. The discomfort is useful. It means your intuition has reached the edge of its territory. When people hear the word edge, they immediately imagine a spaceship flying toward it, headlights on, instruments blinking, until suddenly there is a barrier. But that picture is too childish for what cosmology is actually asking. The edge of the universe, if such a phrase even survives careful thought, would not be like the edge of a table. It would be more like discovering that the rules you use to define distance, direction, and continuation stop applying in the way you expected, not because reality becomes fantasy, but because your old picture was too small. So I am not going to ask you to believe the universe has an edge. That would be just another lazy certainty. I want something better from you. I want you to hold the question open without rushing to close it, because the most interesting part of science is not when you defend the picture you already had. It is when you discover that the picture was never as solid as it felt. And once you see that, the night sky changes. It is no longer just a vast black ceiling sprinkled with stars. It becomes evidence. It becomes a question written in light, and the word infinite, which once felt grand and final, begins to sound suspiciously like something we said because we were not yet brave enough to ask what the universe is really doing. If you want to know the shape of the universe, do not begin by drawing a picture of it in your head. That is a dangerous place to start, because your head is filled with furniture, roads, rooms, and little Euclidean habits that work perfectly well for crossing a street, but were never designed to measure the cosmos. Begin instead with light, not the light from a nearby star, not the light from a galaxy shining proudly across the dark, but the oldest light we can still receive, the faint afterglow left from the time when the universe was young enough to have no stars at all. There was a period when the universe was not transparent. I want you to imagine that carefully. It was not empty darkness waiting for galaxies to appear. It was hot, dense, crowded with charged particles, and light could not travel freely through it. A photon would move a little way, strike an electron, scatter, move again, scatter again, trapped in a glowing fog where every direction was confusion. The universe was full of light, but no one could have seen through it. That is a strange sentence, but it is true in the most physical sense. Then the universe expanded and cooled. Electrons and protons finally joined into neutral atoms, and suddenly the fog lifted. Light that had been trapped was released, and it has been traveling ever since. Stretched by the expansion of space until today, it arrives as microwave radiation from every direction in the sky. This is the cosmic microwave background, and I do not want you to think of it as just a technical term. Think of it as the baby photograph of the universe. Not sharp, not colorful, not sentimental, but real. A fossil made of light. What amazes me is not only that this light exists, but that we learn how to read it. Imagine holding an old, damaged photograph and discovering that the tiny stains on it tell you the size, age, composition, and geometry of everything. That is almost what happened. The cosmic microwave background is not perfectly smooth. It has tiny temperature differences, so small you could miss their importance completely. But those small differences are the whole treasure. In physics, the universe often whispers its secrets. It rarely shouts. Those faint variations came from pressure waves moving through the hot early plasma, a kind of cosmic sound before there were ears, before there were atoms arranged into bodies, before there were planets where anyone could ask questions. These waves could only travel a certain distance before the universe became transparent. That distance left a characteristic pattern in the microwave background, a preferred scale stamped into the oldest light. Now here is the beautiful trick. The apparent size of that pattern on the sky depends on the geometry of space. If space were positively curved, like the surface of a sphere, the pattern would appear magnified. If space were negatively curved, like a saddle, it would appear smaller. If space were flat, it would appear at just the angular size predicted by ordinary geometry. So we do not simply ask space what shape it is. We let ancient light cross it for nearly the entire age of the universe, then examine how the pattern arrives. And the answer from our best measurements is that space is extremely close to flat on the largest scales we can observe. A cosmic triangle would have angles adding to 180 degrees, not because someone preferred simplicity, but because the microwave background says so, that is the important difference. This is not imagination dressed up as certainty. This is evidence extracted from a radiation field colder than your breath and older than every star you have ever seen. But you must be careful here. The result is powerful, but it is not the result many people think it is. Flatness tells you about curvature. It tells you how space behaves locally and across the observable region. It does not automatically tell you that space continues forever. That extra step is a temptation, not a measurement. And this is where many minds quietly slip. They hear flat, and they smuggle infinite into the sentence without asking permission from the data. The oldest light has given us a map, but not the whole territory. It has shown us that the visible universe is astonishingly smooth, ancien, and nearly flat, yet hidden inside that answer is a sharper question. If space can be flat without proving it is endless, then what else have you been assuming just because the word felt familiar? The moment you hear that the universe is flat, something in you relaxes, almost as if a difficult problem has quietly solved itself in the background. Because flatness feels familiar. It feels like something you already understand from everyday life, like a road stretching ahead or a sheet of paper lying still on a table. And from that feeling, it is very easy, almost automatic, to take one more step and conclude that space must go on forever, that flatness guarantees infinity, that if you keep moving in a straight line, you will never run out of room. But that last step does not come from physics, it comes from habit. And the trouble with habit is that it rarely announces itself. Let me show you where that intuition slips. Not with something abstract, but with something you can almost hold in your hands. Imagine a perfectly flat sheet of paper. No curvature, no bending, no distortion. Draw a triangle on it, and the angles add up to 180 degrees. Just as you were taught, everything behaves exactly the way flat geometry says it should. Now, if that were the only thing you knew, you might say, this could go on forever, because nothing in that local behavior tells you where it ends. But of course, the paper does end. You can pick it up, turn it over, find the boundary. It is flat, and it is finite at the same time. Now do something slightly more interesting. Take that same sheet and roll it into a cylinder, not stretching it, not compressing it, just connecting one edge to the other. Suddenly, something changes in a way that is easy to miss if you are not paying attention. Locally, nothing has changed at all. If you draw a triangle on the surface, the angles still add up to 180 degrees. Parallel lines still behave as you expect. Every small region looks just like a flat plane. But globally, the structure is completely different. Because now, if you travel far enough in one direction, you do not encounter a boundary. You return to where you started. The space has wrapped around itself. I remember the first time I really tried to take that idea seriously. Not as a classroom exercise, but as a model for how space itself might behave. And what surprised me was not the mathematics, which is quite straightforward once you learn the language, but the resistance I felt trying to picture it. My mind kept insisting on imagining the cylinder sitting inside a larger space, something I could step outside of and look at from a distance. But that is not part of the description. That is something I was adding because I am used to thinking about objects embedded in a bigger environment. And once you notice that, you begin to see how often your intuition relies on pictures that are not actually required by the physics. This is where an important distinction appears, one that people often blur without realizing it. Geometry tells you how space behaves locally, whether it is curved or flat, how distances and angles relate in small regions. Topology tells you how space is connected globally, whether it loops back on itself, whether it has a finite extent, whether you can travel indefinitely without encountering a boundary. And these two things are independent. You can have flat geometry with a topology that makes the space finite. That is not a contradiction. It is a possibility built directly into the mathematics. So when we say the universe is flat, we are saying something precise but limited. We are describing the curvature, the way space behaves on the scales. We can measure. We are not yet describing the full global structure. The universe could still be finite, still have a total size, still possess a topology that closes in on itself in ways that are not obvious from local measurements, and that is where the simple picture of endless space begins to crack. Not dramatically, but quietly, the way a familiar idea starts to feel less certain once you look at it from a different angle. At this point, you might feel the urge to ask a very reasonable question. If the universe is finite, where is the edge? And that question carries with it all the weight of your everyday experience. Because every finite thing you have ever encountered had a boundary, a place where it ended, a surface you could point to and say, this is where it stops. But the examples we have just walked through should make you hesitate. Because a space can be finite without presenting you with an edge in that sense. You do not fall off the cylinder. You do not reach a wall. You simply keep moving and eventually find yourself back where you began without ever encountering a boundary. What makes this more than a mathematical curiosity is that nothing in our current understanding of physics forbids the universe from having that kind of structure. General relativity allows it. The observations we have made do not rule it out. In fact, some hints in the data suggest that the universe might have a characteristic scale, a size beyond which certain patterns do not exist. Though the evidence is not yet decisive, but the important shift has already happened. You no longer have the right to assume infinity just because the space is flat. And once that assumption slips away, something else changes with it. The idea of traveling forever in a straight line without ever returning, without ever encountering any limit, starts to look less like a certainty and more like a story we told ourselves, because it fit our intuition. Physics does not forbid that story, but it does not require it either. And when a story is no longer required, you have to ask yourself whether you are holding on to it because it is true or because it is comfortable. Up to this point, you could still hold on to a certain sense of order, because even if the universe might be finite, even if space might wrap around in ways your intuition struggles to picture, the underlying story still feels clean. The equations work. The observations line up. The universe behaves like something that, at least in principle, you could fully describe. But that feeling begins to shift the moment you stop looking at the cosmic microwave background as a concept and start treating it like data. Because data has a way of refusing to cooperate with the stories we prefer. When physicists built the standard cosmological model, they did not just describe what the universe looks like. They predicted how it should behave in detail. Not vague statements, but precise statistical patterns, especially in the cosmic microwave background. Those tiny fluctuations in temperature that carry information from the early universe, and for the most part, the agreement between theory and observation is almost unsettling in its accuracy, like solving a puzzle where every piece fits exactly where you expect it to, leaving you with the quiet confidence that you have not only understood the picture, but captured something essential about reality itself. But then you look at the largest scales, the broadest patterns spread across the sky, and something doesn't quite sit right. Not in a dramatic, headline-grabbing way, but in a persist, nagging way. like a small inconsistency that refuses to disappear, no matter how many times you check your work. Because the amplitude of those large-scale fluctuations is lower than predicted, the universe appears quieter than it should be, as if the biggest waves you expected to see were somehow missing. And this is not a one-time anomaly. It has shown up again and again across different experiments, different instruments, different analyses, each time subtle, each time easy to dismiss on its own, but difficult to ignore collectively. I once spent weeks chasing down an inconsistency in a set of measurements that, on paper, looked too small to matter, the kind of thing most people would round away and move on from. But the more I tried to eliminate it, the more stubborn it became. And what stayed with me from that experience was not the final answer, but the process, the uncomfortable realization that the moment you decide something is insignificant without fully understanding it, you stop doing physics and start doing storytelling. And the universe is under no obligation to respect your narrative preferences. So what does it mean for the universe to be quieter than expected at the largest scales? And this is where a simple physical idea becomes surprisingly powerful. Because if you take a system with a finite size, whether it's a room, a cavity, or anything that supports waves, there is always a limit to the wavelengths it can sustain. Waves longer than the size of the system simply do not fit. They cannot form stable patterns, and as a result, the spectrum of possible fluctuations is cut off at large scales, not because something is actively suppressing them, but because the space itself does not allow them to exist. Now translate that into cosmology. If the universe has a finite extent, or even a characteristic scale beyond which its structure changes, then the largest possible fluctuations would be limited, and what you would observe is exactly what we see: a suppression of power at the largest scales in the cosmic microwave background. A kind of absence that only makes sense if something about the size or structure of the universe is imposing a constraint, and suddenly the quietness is no longer just an oddity, it becomes a clue. Of course, you have to be cautious, because this is not the kind of evidence that allows for bold declarations. The statistical significance is not overwhelming. The possibility that it is a fluctuation of chance is still real, and there are alternative explanations that do not require changing the global structure of the universe. Subtle systematic effects, foreground contamination, or simply the fact that we only have one universe to observe, and randomness at large scales can look misleading when you have only a single sample. So physicists argue, reanalyze, refine their methods, and push the data as far as it can go without over-interpreting it. But the discomfort remains, not because the anomaly is definitive, but because it is consistent. It refuses to vanish under scrutiny. And it is not alone. There are other large-scale features: asymmetries in the distribution of fluctuations, regions that are colder or hotter than expected, patterns that do not quite fit the idea of a perfectly uniform, isotropic universe extending without limit. And each of these on its own might be dismissed, but together they begin to suggest that something about our simplest assumptions might be incomplete. And that is where things become genuinely interesting, because physics advances not when everything fits perfectly, but when it almost fits, when the model works well enough to trust, but poorly enough to question. And the cosmic microwave background, for all its elegance and precision, is beginning to whisper that the largest scales of the universe may carry information we have not fully understood. Information about whether space truly extends without bound, or whether there is a deeper structure, a limit, a scale that we are only just beginning to notice if you follow the clues far enough back, past galaxies, past atoms, past, even the moment when light first became free to travel, you run into a period where the universe behaves in a way that almost sounds unreasonable at first hearing, because instead of expanding at a steady pace, it expands explosively, exponentially, so rapidly that distances between points in space grow by factors so enormous that the word fast stops being useful. And this idea, called inflation, was not invented to make the story more dramatic. It was introduced, because without it, several features of the universe simply do not make sense. The uniformity of the cosmic microwave background, the near-perfect flatness of space, the absence of large irregularities on vast scales, all of these are explained if, in the very early universe, space itself underwent a brief but extraordinary period of expansion that smoothed out any initial irregularities, the way stretching a wrinkled fabric smooths out its creases. And for a long time, that was the end of the story. Inflation did its job, explained what needed explaining, and then quietly stepped aside. But that tidy version only holds if you treat inflation as something that turns on and off cleanly everywhere at once. And the moment you take quantum mechanics seriously, that picture begins to fall apart. Because the field responsible for driving inflation is not a perfectly controlled classical system. It fluctuates. It behaves probabilistically. And those fluctuations mean that inflation does not end uniformly. In some regions it stops. In others it continues. And once you accept that, you are led almost inevitably to a very different picture of the universe. Instead of a single uniform expansion ending everywhere simultaneously, you get pockets, regions where inflation has ended, and the familiar physics of particles and forces takes over. Embedded in a larger background where inflation continues and these regions grow, evolve from structure, become what we would call universes, while the surrounding space keeps expanding, producing more regions, more pockets, more domains where different conditions may arise. And this process does not necessarily stop. It can continue indefinitely, generating a vast, possibly unbounded collection of these bubble universes. The first time I followed that logic all the way through, I remember feeling a kind of quiet shift, not because the idea was extravagant, but because it felt almost too natural, as if once you allowed quantum mechanics into the story, you had no real choice but to accept the consequences, and the consequence is that what we call the universe may only be a small part of a much larger structure, a local region where inflation happened to end in a particular way, giving rise to the conditions we observe. And now, for the first time, the idea of an edge begins to take on a concrete, though still subtle, meaning, because in this picture, our universe does have a kind of boundary, not in the sense of a physical wall you could approach, but in the sense of a transition, a surface separating two different regimes of behavior. On one side of the region where inflation has ended and space evolves according to the familiar laws of cosmology. On the other, a region where inflation continues, where space is still undergoing that rapid, exponential expansion. This is not an edge you could reach by traveling, because it is not located somewhere in space waiting to be discovered. It is part of the history of how our region of space came into being, a boundary in time and process rather than in distance. And that distinction matters because it forces you to rethink what you mean by inside and outside, since the usual geometric intuition no longer applies in the same way. What makes this picture even more intriguing is the possibility that different bubble universes might not all share the same physical properties, because the way inflation ends could vary from region to region, leading to different values of fundamental constants, different particle masses, perhaps even different effective laws of physics. And if that is true, then the universe is not just large, it is diverse at a level that goes far beyond anything we experience directly, a landscape of possibilities rather than a single uniform reality. At first, that can feel like a loss of simplicity, as if the universe has become too complicated to grasp. But there is another way to see it, because every time science has expanded our view, every time we discovered that what we thought was the whole was only a part, the result was not confusion, but a deeper understanding of where we fit, from Earth to solar system, from solar system to galaxy, from galaxy to cosmic web, and now perhaps from universe to something even larger. So when you ask whether the universe has an edge, one answer emerging from this line of reasoning is that it does, but not in the sense your intuition first demanded. It is not a boundary you could collide with or observe directly. It is a limit defined by the conditions under which our region of space formed. And once you see that, the question shifts. It is no longer about how far you could travel, but about how many layers of structure reality might contain beyond the one you currently inhabit. Before we go any further, I want you to pause and think about something so ordinary that you almost never question it. A glass of water sitting on a table, because you've seen it as a liquid, you've seen it freeze into ice, you've seen it boil into vapor, and none of that surprises you anymore. Yet if you look closely, it should, because nothing about those transformations is trivial. The same collection of molecules rearranges itself, and suddenly the behavior changes completely. Flowing, rigid, invisible, and the transition between those states is not a slow blending, it is abrupt, governed by precise conditions, a shift from one phase to another. Now here is the uncomfortable step, the one that does not feel natural at first, because it asks you to take that everyday idea and apply it somewhere you never expected. What if space itself is a phase, not a fundamental backdrop, not the stage on which physics happens, but a particular organized state of something deeper, something that, under the right conditions, behaves like the smooth, continuous geometry you experience, but under different conditions might behave in a way that no longer resembles space at all. I remember the first time I tried to take that seriously, not as a philosophical curiosity, but as a physical possibility, and the resistance was immediate, because it feels like you are removing the one thing you thought you could rely on. Everything else in physics happens in space. Every position, every motion, every measurement depends on it. And now you are being asked to consider that it might not be the foundation, that it might emerge the way temperature emerges from the motion of molecules. Something real, measurable, but not fundamental. In several approaches to quantum gravity, this is not just speculation. It is a working framework. The idea that at extremely small scales, space is not continuous. It is built from discrete elements, tiny units that connect in a network, and what you perceive as smooth geometry is what happens when you average over an enormous number of those elements, much like the surface of the ocean appears smooth from a distance, even though it is made of countless individual molecules moving in complex ways. And if that picture holds, then space is not the base layer of reality. It is a large-scale approximation, and once you accept that possibility, even tentatively, the meaning of an edge changes again. Because now you are no longer asking where space ends in the sense of a boundary you could reach. You are asking under what conditions the phase we call space ceases to exist, and that is a very different kind of question. It is no longer about distance. It is about structure, about whether the underlying system continues to organize itself in the way that produces geometry. So what would it mean for space to stop existing, not as a dramatic collapse, not as a wall or a void, but as a transition, the way water becomes vapor, the way a crystal loses its structure when heated? It would mean that the concepts you rely on, distance, direction, location, would stop being well-defined. Not because something is hidden beyond them, but because they belong to a phase of reality that is no longer present. You would not step outside space because stepping requires space. You would simply reach a point where the description itself fails. I once tried to explain this to someone using an analogy that felt clumsy, even as I said it. Imagine trying to describe a solid object using only the language of fluid flow. You can talk about currents and turbulence, but at some point the words stop matching the system. Not because the system is mysterious, but because the framework is wrong. And that is the kind of mismatch we might be facing when we ask what lies beyond the edge of space in this picture. What makes this more than philosophical speculation is that it leads to testable ideas. If space has an underlying discrete structure, then at extremely high energies or over enormous distances, the smoothness of space might begin to break down in subtle ways. Light might propagate differently. Signals might arrive with tiny deviations that hint at a deeper structure beneath the apparent continuity. And physicists have been searching for these effects, looking for any sign that the fabric of space is not as smooth as it appears. So far, the evidence has not revealed such deviations, which tells you something important. If space is emergent, it is extraordinarily stable across the scales we can probe, holding together with a consistency that makes it indistinguishable from something fundamental, at least within the limits of our current experiments. But stability is not the same as fundamentality, and the absence of evidence here does not close the question. It simply pushes it to deeper levels, and that is the shift that stays with you. Not a specific model, not a single equation, but the realization that the thing you thought was the stage might itself be part of the performance. That space could be something that forms, persists, and under certain conditions, dissolves. And once you begin to see it that way, the idea of an edge stops being about how far you can go and becomes something more subtle, a question about where a particular way of organizing reality gives way to something your current intuition is not yet equipped to follow. But now, the question you started with has quietly changed shape without asking your permission, because you thought you were asking about distance, about how far space extends. But what you've really been doing is pushing on the limits of the language you use to describe reality. And the deeper you go, the more you begin to notice that the difficulty is not just out there in the universe. It's in here, in the way your mind insists on framing the problem. You keep wanting to ask it, and I know you do, because I did the same thing. What is beyond the edge? It feels like the most honest question you can ask, almost like refusing to accept an incomplete answer. But there's a subtle assumption hidden inside it. One. So natural you almost never notice it. And that is the assumption that beyond is a place that if something has an edge, there must be something on the other side. Another region, another extension of space waiting to be described, but everything we have uncovered points in a different direction. not toward a larger container, but toward the idea that space is not sitting inside something else. It is the thing being described, and once you take that seriously, the question begins to loosen. Because if space itself is what you are talking about, then asking what lies beyond it is like asking for a direction that may not exist, not because the universe is hiding something from you, but because the concept you are trying to use has reached its limit. I remember struggling with this kind of boundary, not in cosmology at first, but in trying to understand systems where the usual intuition simply refused to work. And what I kept doing over and over again was trying to force a picture, trying to imagine something I could place in a mental space. Dra, rotate, examine from different angles. And every time I did that, the idea collapsed. Not because it was wrong, but because I was insisting on using a framework that no longer applied. And it took a while before I realized that sometimes the problem is not that you do not understand the answer. It is that you are asking the question in a language that cannot express it. If space is emergent, if it arises from something deeper, whether it is quantum geometry, entanglement, or something we have not yet fully uncovered, then the edge of the universe is not a location. It is a limit of description, a place where the concepts of distance and direction lose their meaning, not because reality ends, but because the tools you are using to describe it stop working in the way you expect. And that is a very different kind of boundary from anything you have encountered before. There is something unsettling about that, because it removes the comfort of a picture. You cannot imagine stepping outside the universe and looking back at it. You cannot place it inside a larger space and ask what surrounds it. And yet there is also something deeply satisfying about it, because it tells you that the universe is not constrained by your intuition, that it does not need to fit into the categories you developed from everyday experience, and that when those categories break down, it is not a failure. It is an invitation to think differently. What fascinates me is how we arrived at this point, not through speculation alone, but through measurement, through observation, through following the consequences of our theories wherever they lead, even when they take us somewhere uncomfortable, because physics has always had this quality. It does not ask what feels right. It asks, what is consistent? And when consistency forces you to abandon something that once seemed obvious, you have to be willing to let it go. So when you ask how big the universe is, the answer is no longer a single sentence. It unfolds in layers. The observable universe has a finite size. Beyond that, there is more we cannot yet see. The geometry appears flat, but does not guarantee infinity. The topology may close in on itself. Inflation may place our universe inside a much larger structure. Space itself may be an emergent phase. And the idea of an edge may not refer to a place at all, but to the boundary where your current description stops applying, and at some point, the question stops being about the universe alone and starts turning back toward you. Because what you are really confronting is not just the scale of reality, but the limits of your own way of understanding it. And those limits are not fixed. They have moved before, they will move again. Every time you are willing to question what once felt obvious, you began with a picture that felt complete, an infinite expanse stretching without end. And now that picture is fractured into something far more subtle, something that refuses to be summarized in a single image. And that is not a loss. It is a gain, because instead of closing the question, you have opened it. And in physics, that is where the real work begins. Not with answers that feel final, but with questions that refuse to disappear